vấn đề bị không?
Hi everyone, welcome to the Microsoft Database Lecture Series. So today we have the honor of having two visitors from Microsoft talking about query optimization for database applications. So Karthik Ramachandra comes from Microsoft Research India and did a bunch of work in query processing and also database application optimization. And together with him today is also Kwon Yoon Park from the Jim Gray System Lab from Madison. So please take it away.
Thank you. Yeah, I would like to thank Alvin and for hosting me and giving me an opportunity to come and talk about Froid here. If there is, I would like to keep this interactive, so feel free to stop me anytime in the talk if you have any questions. So this is work that we've been doing for the past almost 3 years now. So I put my affiliation as both the Gray Systems Lab and Microsoft Research India, because so most of the work on this Froid project happened while I was at the Gray Systems Lab. And now I have moved to MSR India, and we are still continuing to collaborate and continue this project. So, and this is joint work with a bunch of people. Kwon Yoon Park is here. You can ask the hard questions to him. Alan and Kwon from the GSL lab, and Venkatesh had interned with us a couple of years ago in summer. And Cesar and Connor are the SQL Server product team, the engineering teams. Where is? Oh, it's in Madison, Wisconsin. Yeah. All right. So with that, let me start off with a story. So this is a story of two engineers in an e-commerce company. Let's say like Amazon or Walmart, or let's say one of those. So typically, you know, they have these e-commerce companies might have data about their customers and orders. I'm just giving some example here. And there is a manager who owns this database and is responsible for doing some analytics on these kinds of on this database. Now they want to introduce, let's say they want to introduce some rewards program, and so basically they want to classify their customers into 3 categories: platinum, gold, or regular. And there is some logic for how you do it. So basically, if the customers have placed orders worth some amount or more, then they are platinum. Otherwise, they are gold or regular, right? So it's a simple definition of customer classification. And so this manager calls 2 of her engineers in her team and says, "Go build this for me," right? So it turns out that these 2 engineers get into a fight about how to implement this. So they have 2 different opinions. So they go off on their own and they say, okay, I do my thing, you do what you want to do. And so what happens is that one of them, it turns out, he's a SQL expert, right? So he writes one complex SQL query which does this job, right? But probably only he can understand the query. But the other person, the other engineer happens to be a programmer who's not expert in SQL, but he knows some basic SQL, but he knows programming in like procedural languages, like let's say, in this case, I'm showing T-SQL, the transact SQL. But he writes a simple function which computes the service level. By service level is basically whether the customer is platinum, gold, or regular. As you can see, the UDF, or this is called as a user-defined function, where from an SQL query, you can call this function. And then this function is right now returning the service level, which is a string. The way it does it is it's basically computing the total price of all the orders made by a customer, and it just uses some if-else to check the thresholds and decide the category, right? Of course, yeah. So just to note, this example program itself is taken from an earlier paper of ours. Right. So the programmer, thinks that this is his solution is a better one for a few reasons, right? So he thinks, he sees that these UDFs encourage modularity. You can keep your code modular. You can reuse this code if you want the same function from a different query or a different context. It's you don't have to duplicate any code, and also it's easier to express and read for people who don't understand complex SQL. like these kind of business rules especially, and even some ML algorithms could be more intuitively expressed using imperative programs like this. So with this, they both come to the manager with their respective solutions and present it to her. And both are hoping for a promotion, right? Because they have done their best. So the manager basically runs both of these on their database, and turns out she decides to fire one of them and promote another. So this is pretty drastic, but can anybody guess who was promoted and who was fired? Yeah.
I'm betting the SQL optimizer should have gotten a promotion.
Okay. Anybody wants to contradict that, or no? And why? Can you say why that could be the case?
I should imagine a lot of man hours have been put into the SQL optimizer compared to the optimizer for
Sure. Okay.
But I don't think they would fire the SQL guy because he understands the SQL query, versus, as you said, the other one can be understood by anyone.
So you're saying the SQL expert will be fired?
No, he will be kept. The programmer will be fired.
Because?
You said that like the SQL query, only the SQL programmer.
Oh, I see. So, yeah. That's a way of ensuring your job security, right? Yeah, exactly. Yeah. Yeah. Fair enough. So as both of you said, the SQL guy was promoted and the programmer was fired. The reason turns out to be slightly, you are along the lines of the actual reason. When the manager ran this program, the SQL query ran in a couple of minutes, whereas the function took a few hours to run, and that was not acceptable to their business requirement. And that's why this happened. So the point to note is that UDFs, or these kinds of imperative functions, come with a lot of benefits, but those benefits come with a huge performance penalty today. And this is true for all relational databases out there, not like pointing at any single one. So okay, with that story background, right, now let's move on to the little bit of a detail about why UDFs end up being so slow in databases today. The main reason why UDFs are slow is that query optimizers don't know about UDFs. They treat UDFs as a black box during query optimization. Not only that, they do not know how to cost the UDF, because query optimizers are all built upon this cost-based optimization. Yeah.
UDF stands for user-defined function.
Yes, user-defined function. Yeah. So query optimizers are today's optimizers use a cost model to determine how each operation is, and then decide the best plan for a query. It turns out they don't cost user-defined functions, so they think it's sort of an inexpensive operation, which is definitely not true in this case. And you can also think that you may parallelize this. Why not run this in parallel? It's not straightforward. It's possible, but it's not straightforward, especially because of these kind of queries that exist inside the UDF. So you have to decide how many threads to give for each individual query that is inside the UDF, and you need to figure out. It's hard to come up with an optimal parallelization strategy for this. So as a result, when you have complex user-defined functions like this inside let's say the select clause like I've shown here, or it could be even in the where clause in a SQL query. This leads to like what we call as R-bar execution in SQL world, which stands for row by agonizing row, which is another way of saying you're iterating over every row and trying to do this instead of doing a set-oriented operation. Row by agonizing row. This is more inefficient if the UDF in turn has queries because of these implicit joins. So let me just describe that here, right? So here, as you can see, we are calling this function service level for every tuple in the customer table, right? So for every tuple, we pass the customer key, and then what this function is doing is that it's looking up all the orders made by that customer, and then computing the sum of total price. So a database person will be able to see that this is actually a join between customer and orders, and a group by on customer key using with this aggregate function. but this is implicit through function invocation. There is no explicit join in this program, right? But since the optimizer if it does not look inside this UDF during query optimization, it cannot figure out that there is actually a join that could be done here. As a result, it results in like an inefficient query plan. And another point to note is that the way UDFs are evaluated is that for every tuple you call this function, and it basically interprets each statement. So it's like an interpreted execution, and so there is no cross-statement optimizations like what a compiler would do typically on such imperative programs. Right? These are some of the reasons why UDFs are really poor in performance. So then the obvious question is, okay, if this was there, why was this not addressed all these years, right? So as we know, right? So UDFs, it turns out they are imperative programs, but as I will show in the subsequent slides, they are very similar to nested subqueries. So in some sense, they lie in between imperative like programming languages and in terms of and in databases, right? So this is like an imperative program running inside a database. So this lies in an interdisciplinary sort of area which has sort of received little attention from either community. There are a few related works which I'll talk about later towards the end of this talk. But to summarize, right, the key challenge here is this impedance mismatch between two paradigms. So there is this imperative programming paradigm where you're expressing logic through variables, conditional branching, loops, and things like that. And the relational paradigm which deals with relational algebra and relational operations like joins and aggregates and projections and so on. So the focus of the DB community has been the main focus has been to optimize declarative SQL. To give an evidence for that, right? None of the standard database benchmarks even have a single UDF in them. That shows that that's not really the primary focus of the database community. It has not been so far, at least. And the other side is that you can always argue that why not take compiler techniques that are known and just implement them on the UDFs, and you get all the benefits, right? Like, but as I mentioned, you can't do things like identifying these implicit relational operations which lie between the boundary of SQL and the imperative code. A compiler could try to optimize the UDF in isolation, but if you want to infer these kind of relational operations that are implicit, you need to look beyond just the function itself. So what do practitioners do today is that they have to make a choice. If they want the flexibility and the modularity of the UDFs, they have to give up performance. If they want performance, they are advised to using UDFs in the first place. But yeah, they have been complaining. There's been a lot of articles and complaints on the internet. You'll find it widespread that this is important problem, but has not been solved yet. So with that, I'll tell another story. This is the story of UDFs and also how Froid comes into the picture in terms of a timeline, right? So UDFs are not new. So SQL Server, for instance, introduced UDFs way back in 2000 itself as a way of encapsulating business logic. After a few years, people realized that when it comes to performance, scalar UDFs are evil. And this is not my terms, but these are articles which I've found on the internet where experts, database experts, have written articles which say that these SQL functions are evil when it comes to performance. So much so that we ourselves, as Microsoft, we had to go and advise our customers to not use a feature that we ourselves built. That was sort of ironic in some sense. So this is one of the MSDN blog posts where one of the architects of SQL Server actually said that if you look at the second paragraph, I recommend that users not use UDFs when plan choice is important on big queries and not put subqueries inside of UDFs and so on. So this is 2010, right? So because it does not cost scalar functions and so on. And as a result, the negativity continued. There are more articles. I've just selected a few here. And even much more recently, even in 2016, in MSD and SQL Server blog, we ourselves wrote that UDFs are evil personified and things like that. So, I mean, there's enough negativity about UDFs out there. That's the bottom line point I'm trying to make. People want it, and people have used it. So, yeah, that's an interesting question, right? I mean, it looks like it's something very attractive to users. And what has happened is that if your database sizes are small, you may not see the impact of these performance problems really, right? So maybe when they were introduced way back in 2000, it was not as bad. Maybe, I don't know if the data sizes were okay, or I mean, but then for a product like SQL Server, you cannot just stop shipping a feature, right? You have to support users for using it and so on. And it is an attractive feature which people like to use also. So yeah, I mean, so around a couple of years, around like 2012-13 time frame, I was doing my PhD at IIT Bombay, and the database group at IIT Bombay and IIT Hyderabad. So we started working on an idea to optimize such user-defined functions. And in 2014, we had a paper in ICDE called Decorrelation of UDF Invocations in Queries. This was actually one of the first, first papers that tried to explicitly talk about how you can optimize UDFs inside a database. And then the same year I graduated and I joined the Gray Systems Lab. And in 2015, I got some time to start, playing around with this idea, and I was inspired by the work I had done, and I was looking for an opportunity to, to put my ideas into a product if possible, and that's where Froid was actually born. I started building a prototype of this thing, and yeah, in 2016 we got more people to join, and we built the prototype, and then we started productizing it in 2017. And we had the paper come out, and I moved to India last year. This paper came out in VLDB, and it got some good reactions from people. And eventually, right now I'm happy to say it's actually publicly available as part of SQL Server. It is a feature of SQL Server 2019. Which is currently in beta. So if you can download SQL Server and try this feature out. So we have come all the way from 2000 where UDF to this point where now customers are saying these things. These are customers who have tried out the beta, and this is the reaction that some of which I have curated here, right? So yeah, the last one is especially interesting to read. Sorry.
What is MVP?
Oh, MVP stands for Microsoft Valued Professional. So those are essentially experts who are like partners with Microsoft who get access, and they evangelize some of our and things like that. So that's where we are today. So with that background, now I'll get into the intuition of actually how Froid works and what really happens under the covers. So the key intuition behind Froid comes from two observations. The first observation is that this iterative execution of UDFs, which is like this row by row thing that I talked about, it turns out is very similar to what we call as correlated execution of subqueries. So what do I mean by that? So here is an example of from TPCH schema where we are trying to find the minimum cost suppliers for each part. So here there is a outer query in green, and there's a blue subquery, nested subquery. Where we are trying to, and there is this correlating parameter called which is p1.partKey in this example, where from the outer query you pass a parameter and then you evaluate the subquery and then evaluate the predicate. So a correlated execution strategy says for each tuple in the green query, evaluate the blue query and then proceed, right? So that is called as a correlated evaluation, and this is considered to be an inferior strategy in subqueries, because you're doing like a row by row iterative way of execution. So databases have evolved mature techniques to optimize subqueries. This is a well-studied topic in literature as well as in practice. There are all the mature databases have a good subquery optimization strategy in them. And to give an example of SQL Server, correlated subqueries in SQL Server are modeled using what is called as the apply operator, which was introduced in 2001 specifically for this purpose, to model subqueries in an algebraic form as a relational algebra operator itself. So how it works is that formally it is similar to a join. It is like a higher order join in some sense. So it accepts two inputs, E0 and E1, and for each tuple in E0, you evaluate E1, which is E1 is a relational expression which is parameterized by the tuple from E0, right? So I'll give an example to clarify this further, and then so okay, yeah, I have the verbal, yeah.
This is also called a dependent join sometimes.
Yes, or I think in ANSI SQL they call it lateral join. I think some databases use that as the syntax, and SQL Server uses apply, and yeah, dependent join is also another name for it. Yeah, right. So then you combine this E0 and E1, or this tuple from E0 and E1, using the join type, which is a parameter to this thing. So you can parameterize with any join type. It could be cross product, left outer join, and so on. So to give it for this example, if you look at here, right? So I have so the left child is the green color, which is the outer query. This is from P1 is coming from the outer query, and this right subtree of this apply operator shown here using this A. This right subtree forms the blue subquery. So there is this correlated parameter-based filter here, and then you model this using this apply as a apply cross. So here is being used. Cross product form of apply is being used. So what we did here is basically took the subquery and modeled it as a relational algebra operator, which can fit into this tree structure that we would like. But what does that buy us? Once we express these subqueries using apply, you can simplify them using some algebraic rules, which are defined again in that paper that introduces the apply operator. There are rules, and in many cases you can remove this correlation between the outer and inner query, and in which case you can remove the apply operator and replace it with a standard join or a relational operator. So to give the same example as I showed in the last slide, SQL Server today, if you write a query like this, the optimizer can do this transformation, where you can see on the right side there is no apply, and there is no correlation between the left and the right here. So it has figured out that this is a join, and it has figured out a group by part key, and so this plan is now a set-oriented join, and this is a set-oriented plan which can be easily parallelized, and different strategies can be used, and this is called as the decorrelated subquery, and this is called as subquery decorrelation, which is the core technique behind optimizing subqueries. Right. So this is the background, and what we are saying here is that this same technique can be extended to handle UDF invocations also, not just subqueries, but UDFs also. This was initially shown by that paper that I was mentioning in ICDE 2014, and we build upon that idea. So to summarize the intuition, what we are trying to say is that if we can take an imperative user-defined function and express the entire body of that function as a single relational algebraic expression, or an SQL query, if you will, then any query that calls this function will be seen as a query with a subquery which is equivalent to this function, right? So once you can express it a UDF as a subquery, then you are in familiar territory. Then the optimizer can do all its subquery optimization techniques that it knows. So then the crux of the problem now becomes how can you take a imperative user-defined function and express it as a single algebraic expression. So that from the rest of my talk is about how do you open up the black box user-defined function in a systematic way so that the optimizer can play its tricks on it. So again, I'm using the same example, but a simplified one. There is only platinum and regular here. I've removed the gold for simplicity. Right. So I'll just give a walkthrough using this example. So the first step that we do here is that we show. We can see that every imperative statement can be looked at, can be translated to a relational equivalent relational algebraic expression. So here are some examples. So if you have a variable assignment statement, as I've shown here, you can express it in relational algebra as follows, as a projection of a constant variable on a, like here S stands for a single row table, right? So basically this can be seen as a single row, single column relation, where the column name corresponds to the variable name and the value of the variable is the value, is the row, is the one row in that table, right? I mean, this is a logical, just an expression, but just to give some intuition, I'm say this, right? So similarly, if you have a variable, I mean, a query being assigned to a variable, you can do the same thing. You can project it as a column. So the relational expression for that is here. Similarly, for conditional branching, you can use the case expression in SQL to express the same thing as another column again, right? So, so these are just some examples of saying that you can express individual statements as relational expressions. Once you do that, then we expand it to what we call as program regions. So region is similar to a block, or it's like a structured fragment of a program. For example, here this is one region. This is a region of straight line code, and so you can combine the individual expressions we had into a single expression by just having. So this is something like a 2-column 1-row table, if you will, because there are 2 variables that are defined in this region, right? So we end up with this expression which has 2 projections with the value for each of them there. Similarly, for the second block, you have an equivalent expression, and the third block, you have another expression. I'll go to the details a little bit about that, and also about the fourth one. So now, as I was saying, for the first block, you have something like this logically, right? You have a 2-column 1-row table for this. Second block has only one variable that's being returned to, so it has a single row, single column table. And then we combine it using the apply operator at this point. This is the first place where we start using the apply to combine these things. And similarly, we again combine it with the block, with the expression for the third block using the apply. And finally, when we encounter the return statement, we just project out the value of the return variable. So what does this look like in terms of relational algebra? It's another way of saying the same thing. But in terms of the program, right, in terms of SQL query, this is what it will look like. So I've basically put the cross apply operator in between. So what is happening here, if you observe, is that in this this is an expression for region 1. That's why I've called it E_R1, and similarly E_R2 and R3. So if wherever we use, if we want to use a variable that was like, let's take the example of total. So the total variable was written here, and I'm using it in the second block. So basically there is a data dependency. So these data dependencies can be preserved because now you have this aliasing mechanism and this whole dependent join thing, which will allow you to use the value of a variable here in the subsequent block. So I'm using the E_R1.total, which will give me the value from the previous block and so on. So we can preserve all the data dependencies using this apply operator to stitch together these individual expressions into one expression. Yeah.
Besides the regions, so for example, here you decide to put them like the total and the level into one table because you're grouping several statements together. Yeah.
So the regions are actually a standard technique used in compilers also. The way you define a region is that there's a straight line basic block is a region, and a conditional block, which is actually these regions are a hierarchical concept. So the entire program is a region. I have simplified it here for the purpose of the talk, but the entire program is a region which can be composed of a sequential region and a conditional region and so on. And the conditional region in turn has a small sequential region inside it. So that's a standard way to construct these regions from any given structured program. If you have things like goto, you may not be able to construct these regions as in a straightforward way, but this is for goto free programs.
So every region will generate one table. So if there are multiple variables, and then they will put into one table.
Yes, exactly.
I think the confusion comes from region 1. So in region 1, you decided to compute both the level and the total.
Yeah.
But you could have split this into 2 regions. The first one computes the level, the second
Yes,
one computes
you
the
could.
level.
You could. I mean, at a base case, you can take each statement as a region, and have one for each statement also. It's functionally that is right, but we want to try to reduce the size of the expression that we are building, and that's actually the reason we try to combine as many as we can into a single expression.
And if you do a region for each statement,
Sorry.
even if you were to do a region for each statement, it seems like your rules of cross apply would handle that.
Yeah, it will handle that. Yes, exactly.
You can just consider each statement to be a region.
Yeah, we could do that. Yeah, it's in terms of these transformations, it is identical. There's nothing different. It's just that you may have more apply operators in your tree, and the resulting tree might look big.
Optimizer or base.
How large is the UDF in practice?
Yeah, I'll come to that. I have some numbers. I can show that. Yeah, you had a question.
So what happens if we have goto or function call?
Yeah, so goto is something we don't handle. We discourage people from using goto anyway, and we currently, if we encounter any construct that we don't support, we will not do this at all. So we will give up basically. So that's for goto. Nested functions we can still do, because you can think of, if you can convert that nested function into a single expression. If that function is also defined using in some form like this, you can first inline that function or transform that function into a single query, and then use that here to you can combine that with the rest of this thing. So you can just compose the same way we are doing this. So nested functions are okay.
So what happens with the recursive function calls?
Yeah, recursive again we can. So currently what we do is that we have a threshold. So we inline to a particular depth, and then we stop inlining, or we sort of basically convert it to a particular depth, and that is more guided by how big the tree is growing into. So we want to make sure I'll come to some of those limitations later, or the limits of when we stop doing this or when we enable this and so on.
Yeah. Another limitation I wanted to ask about is our global variables.
Yeah, luckily for us, in this context of user-defined functions, right, you can call a user-defined function from a SQL query. It could be a select query or an insert update also, but there is no global state as such. But there is a catch there. Like for instance, you can have inside the UDF, I can call some function, like some built-in functions. Let's say there's a get date or something, right? You get the current date, which is actually like a global variable in some sense, because it's changing outside the scope of this function. It is not it is a, what do I say, side effect. Okay, there are some built-in functions which can cause side effects. Like there is this new ID or something where you are generating an ID sequentially. So every time you call it, you are updating some state. So next time you call it, you get a new number, right? So those kinds of, if you encounter those kinds of side effect causing or time dependent functions, then we have to be careful. So currently we are conservative, and we don't do it, because we may change the semantics if we try to transform those functions. Any other questions so far? Sure.
I understand that you are trying to basically, this is not exactly the SQL query, but do you deal with situations in which a programmer might write this first region that you showed, I don't know, in some naive way? For example, describing this single query using 3 queries, using 3 joins.
Yeah.
So is that the kind of stuff that you also are able to recognize and optimize that it will actually be one query instead of, let's say, 3?
So we don't explicitly do that. Currently, we just, like I said, we just go through these regions and construct the expression. But as I will show you, once we construct the expression on the right side, we can simplify this further. So there are simplifications that I will show on top of that, which may give you the effect of what you are asking for. But yeah, it may not. I don't know if it's like I can guarantee that it will always happen or something. It depends on how the program is written. It could happen, yeah. Any other question? Okay. So yeah, okay. Yeah, just to clarify, what I'm showing here is actually simplified. There are more details when you go to a industry strength implementation. There are many more things to take care of, but I won't be able to get into all that. So after we have this, right? Okay. So this query is now semantically equivalent to this function. So this is one single SQL query, right? Which is probably harder for humans to understand, but it turns out the query optimizer is fine with this. So what we do is we take this query that was calling this function, and in place of this function, we just replace it, we dump this entire query, let's say, right, as a subquery. I've just put this under this parenthesis and made it as a scalar valued subquery in this case. And then we just leave it to the optimizer to take care of it. So, so what does the optimizer do? So here is a small glimpse of what happens. So if we give a relational expression like this, and then but now we have transformed this function call into the expression that I came up with. So as I was mentioning, there are these transformation rules for the apply operator, which are defined in 2001 in one of the Sigmod papers written by Cesar and others, where they show how you can move relational operators above and below the apply while guaranteeing equivalence. And yeah, I won't go into the details, but these rules are fired and they start transforming the tree. And then finally, we get this expression that's shown here. Where, as you can see, there is a left outer join and a group by that has appeared. But I'll show the SQL version of it. I've sort of reverse engineered that into an SQL. So given this input, finally the optimizer output will look very similar to what I've shown on the right side here. So essentially, this is what happens due to the subquery decorrelation optimizations that already exist in SQL Server, right? So the key things to note here is that the implicit join and the grouping has been made explicit. The optimizer has introduced a left outer join and a group by into this. And then now that there is no UDF, or all the operations in the UDF are open inside the main query itself, the optimizer can now cost each of those operations and like plan accordingly. And this plan is now parallelizable. There is nothing stopping from parallelizing it, and there is no function call overheads like there was in the function case. And one other important thing is that we were able to achieve all this without changing the query optimizer at all, right? So for us, the query optimizer was a black box. I mean, we didn't have to touch it. All we did was to change the input to the query optimizer by taking the UDF and translating it into a form that the optimizer can understand. So that is all we did in this process. And so from a productization point of view, or if you want to take an idea and put it into a real product with a history and with a lot of complexity, it's more risky to change the optimizer when you may end up with some intrusive changes that may lead to unexpected consequences. So this is a safe in some sense. Yeah, go ahead.
Do you have results on how long this transformation took?
Yeah, I have some numbers, I think, yeah. But it's a very, as you can see, right, it's a very simple, I mean, it's just a one pass over this.
Right, well, this one's simple, but I could imagine.
It's basically the order of size of the function. I mean, we just make one pass over the function. The bigger your function is, it will take longer, but it's basically one pass. Okay. That's it.
They don't do like recursion in UDFs or anything.
We could have recursion. But I mean, we come up with the expression only once, right? So to come up with, given a function, coming up with an expression for it, or coming up with an equivalent SQL, is just a one pass operation. Yeah, sorry.
Is there any query pattern that generated by your translation that is the optimizer does not have rule to cover that pattern?
So yeah, that's a good question. There are cases. Even forget about UDFs, right? Even in a normal SQL subquery situations, there could be situations where you may not be able to remove the correlation, or where you can express it using apply, but you cannot remove the apply because none of the rules fired. So in those cases, the optimizers, today's databases, they have an implementation for the apply itself. There is a physical operator, which is basically correlated evaluation. So you fall back to correlated execution if it cannot find a way to do set oriented execution. So that is in some sense in terms of the iterative execution part, I think that will be similar to this plan, right? So for every tuple you are calling the function type of a plan, but it may make it like a nested loop kind of thing forcefully, but yeah, that's the fallback if you cannot replace the apply operator. Yeah.
So in practice, did you see any cases where you executed the relational version where it was slower than the UDF version?
We did find some corner cases like that. I'll show some. I have some graphs that show that. So yeah, just to complete my story, the programmer was also promoted because in terms of execution time or in terms of performance, these both are equivalent. So there is no downside to using a UDF now. So there's not only promotions, there is bonuses as well. So just to give us, I have a small example that shows how we can get several compiler optimizations for free by doing the transformations that we did. So here is an example, a type function which accepts an integer, and then using some threshold, it's basically just setting some value, a variable value to high or low, and then doing a string concatenation to return the value. Right? This is just a simple example. So what I'm going to say, so okay, this is what we do, what Froid does. So given this UDF, it will convert it into an SQL query that looks like this. I mean, you don't have to get into the detail of this, but it's basically translated into an apply with case expressions and so on. So now what I'm going to show is that on top I'll show what given this input, what a compiler would have done to optimize this, and what Froid would do, or what as a consequence of Froid, what would happen inside a database. So first step is that this is just examples. So there is this technique called dynamic slicing in compilers, where if you call a function with a constant, or let's say you call it with a compile time constant, it can basically compute the slice of the program that is relevant for that parameter. So in this case, it was called with the value 5000. So it could basically evaluate this predicate at compile time and figure out that all it needs is the true path of the if, and so it could throw away the branching logic completely. So this is what dynamic slicing would do, but any database, if you give this kind of a expression, it will do a simplification which is very similar to that, which gives a similar or same output in some sense. And moving on, compilers do constant propagation and constant folding. These are very commonly used techniques. As you can see here, the value of the variable val is a compile time constant again. So you could propagate that to the return statement and do the string append operation also at compile time, right? So, but it turns out we have, databases do that all the time for SQL queries. Within a single SQL query, if you have opportunities for doing these kinds of propagation, it already happens. And then here at this point, the second statement here and the first two statements are essentially dead code, because the return statement itself is a constant. So it can get simplified using dead code elimination. And our simplification will also naturally lead to the same thing. So essentially, we didn't do anything for getting this part. That's the key takeaway, is that we just had to do this, and we got all this because all these already exist in databases today. That's the key takeaway from this. Yeah, currently we don't do loops at all. I was just coming to that. So moving to some implementation and evaluation. So we support a subset of the constructs in T-SQL, which covers a fairly large number of UDFs in the wild. The main limitation being loops right now, and that is ongoing work. We are working on algebraizing loops also. But we can do all these constructs. And yeah, we have evaluated this on a bunch of customer workloads, which we have got from with an NDA. And also we have taken TPCH. Although TPCH does not have UDFs in them, that the queries in TPCH do not come with UDFs. We have modularized TPCH in some sense. We looked at opportunities where there are similar, where there's the same repeated logic across multiple queries. A simple example being there is this discount calculation in TPCH which appears in queries. So we factored that out into a function, and similarly we created a modular version of TPCH and used that in absence of a benchmark. And we have run this on a decently sized machine, single machine system. So first of all, looking at the applicability of how many UDFs in the wild can we target using what we have today, which is a subset of T-SQL constructs, right? So we looked at Azure SQL DB, which is a SQL Server offering on the cloud. So we looked at the top 100 databases ordered by the number of scalar UDFs that they have. So we wanted to look at databases that use UDFs a lot, right? So we found that in those 100 databases there were about 85,000 UDFs. And out of those we were able to inline. So we call this transformation inlining, if I missed saying that. We are able to inline about 60% of those, which is a huge fraction for us to be able to have an impact. So for more detailed analysis, we looked at the 3 customer workloads. Those workloads had a decent number of UDFs in them, and we were able to inline a very large fraction of those with the current constructs. And the reason why we couldn't do some of the other ones is mainly because of these constructs that we don't support yet, some of which we can, and some of it is because they use some non-deterministic functions or some side effect causing. There are some other conditions which we want to avoid doing this optimization for. So I'll just show a few experiment results. So this graph is on TPCH, and it shows the overheads of introducing UDFs and how we fix it. On the x-axis I have some queries, and the y-axis shows the execution time. So first I'm showing this bar, which is the original TPCH query, which has no UDFs in them, right, as is TPCH. Then this is our modularized TPCH, where we introduced some small UDFs in TPCH, and you can see how the performance nosedives, just because we have expressed the same logic, some of the same logic using UDFs. And then, but here we have not done the Froid optimization. Now with Froid, the third bar shows that we pretty much get back the same performance as though there were no UDFs in the first place. So basically we were able to overcome all the overheads of introducing UDFs. So that's this one. And then this is the overall workload improvement for 2 workloads, 1 and 2. On the x-axis I'm showing the UDFs, and the y-axis shows the factor of improvement. So each bar here represents 1 UDF, and then we have run it using a query like this, a simple query, and we fixed the size of the table to some constant, some value, 100,000 rows here. So you can see that we get like orders of magnitude improvements, like up to 500x and so on.
Can you go back to the last
Sure.
slide?
Yeah.
Why, can you have any intuition behind why with like query 11 and query 22, the Froid actually does better than the original?
Yeah, that's an interesting observation, right? Yeah. So it's interesting because what we, as a result of Freud's transformations, what has ended up happening is we have taken this UDF, or let's compare. Yeah, we are comparing the first and the third graph, right? So there's no UDF, and then we basically we have now rewritten the TPCH query in a different way using some complex subquery now. So it turns out that in an optimizer, right, the different rules get triggered when different patterns in the tree match and things like that. So it's very hard to say which rule actually caused this to. But as an end result, the query plan looks quite different. So if you look at the query plan for this and this, it could be very different. So because the way we have written the query now, right? So that's interesting. I mean, we are still trying to analyze some of those details, but it's very hard because these queries are huge and the plans are huge, and there could be many rules that could have fired which would not have fired before, or which would have fired before and now they're not getting fired. I mean, it's hard to point out.
Right? I mean, that's sort of like a dream, right? Is to be like, we're better after.
Well, but if you see, right, this is log scale. And so it's not really that much. I mean, we are not like doing way better than the original or something. It's very, very small.
You can a little bit of difference.
Yeah. Right. All right, so this was the overall workload improvement, and I'm just going to take one of them, one UDF there, and we'll try to compare how the performance of UDFs vary if you have like larger data sets versus smaller data sets and so on. So again, I'm taking, this is from workload W1, which is a real customer workload. So what we do is we have this query like this: select some UDF with parameters from table T, and we change the size of the table T, right? So here basically the size of the table determines how many times the UDF gets called in this query. So if this table has 10 rows, you will call this function 10 times, right? So we want to see that if the table has different so the cardinality changes, how do the improvements change? So the first one, without inlining, without Froid, as you can see, this is basically linear degradation. I mean, both x and y axis. Oops, sorry, I ran. Both x axis and y axis are log scale here. So this is basically a linear degradation without inlining as the size of the data grows. This one is we have turned on the inlining, but one restriction we have put here is that we didn't enable parallelism. The DOP stands for degree of parallelism. We say that okay, because we are able to inline, it can also parallelize the query, but we want to isolate the benefits due to inlining and due to parallelism. So just to see that, but you can see there are like couple of orders of magnitude improvement, and even in some lower, there is less improvement when you have smaller cardinalities. And then when you enable inlining with parallelism, it turned out in this example, SQL Server continued to choose a serial plan up to 10,000 row table, but when the table grew beyond that, it switched to a different plan, which is why we get another order of magnitude better in terms of latency. So this is basically the how just to vary the give a comparison across the cardinalities. And again, we also get savings in terms of resource consumption. In terms of this graph shows CPU time. So again, from one of the customer workload, we have selected some UDFs. The pattern was the same for all of them. So with Froid off and on, you can see that there is like a huge difference in terms of the CPU time for these queries. Partly because again, if you have a join which you have figured out this is a join, instead you have been doing scans and things like that. So you are reducing the amount of work done in several cases here. So that's why we get this benefit. Even with IO, we do get some savings. I don't have the graph here. But yeah, this is the compile time overhead. Somebody was asking, I think, that how much time it takes to compile. So it relatively, actually this graph is not the best one to describe to you, but relatively compile time increases, right? You get it takes more time to compile because you are doing much more during compilation. But this graph basically shows that that overhead is offset by the execution time savings in all the cases we looked at. So that's what this shows is that this is compilation plus execution time on the y-axis. So this is without Froid and this is with Froid. So here the takeaway is that the overheads are offset by the gains in the execution time. That's primarily. But to give you, I mean, we have some other graphs. I don't have it in the talk, but we do see an increase in the compilation time. It's it's manageable. It's not like too bad or something. So this is a simple. I mean, just no. This is it's a dependency graph that we built. This was not really this was just out of curiosity, to be honest. This was not something we wanted to do something with. It was just a curiosity. We looked at a customer workload. It was quite complex. So we wanted to look at what kind of dependencies exist. So let me give you the legend. So what is in orange are all TVF stands for table valued functions. So the orange is all table valued functions or stored procedures or views, which is out of our scope right now. We're not trying to do anything there, right? And the green ones are all the scalar UDFs that are inlineable with what we offer today, and the red ones are the ones which we cannot inline today with our feature, right? So with this, what we looked at is we saw some interesting things. Is that if you look at this one UDF here, which is green, if I zoom into it, right, so you can see the number of lines that is coming out of it. So this means that there are like hundreds of other views or procedures or functions that are calling this, and the impact of inlining one function could have an impact on all these callers also, right? So it's hard to say what is the impact of inlining a particular UDF. It's an overall impact on the workload that we can look at, and it could be really intricate like this. So yeah, just to before concluding, I'll just briefly talk about some of the related work. As I mentioned earlier, like there are several subquery optimization techniques which we build upon, right? So that our whole technique is dependent on having a subquery optimization framework ready. But some of the most closest related work is the work by Alvin, which came out in PLDI a few years back, right? So the query by synthesis technique. So this one, I mean, I don't have to describe, but essentially uses program synthesis to come up with a equivalent SQL query for a program fragment. Mainly focuses on ORMs, but it's pretty much the similar goal as Froid in an abstract sense. It's very powerful, but in our case, when we tried it out on the different functions, right? In the case of UDFs, we encountered functions with thousands of lines of code and so on. So it's mainly the challenge was about the optimization time. So since we wanted to try to put this as part of the query execution lifecycle, and we have tight budgets on how much time and resources we can give to query optimization. So with that constraints, it seems to be not the right fit for the problem that Froid is trying to address. But in an offline setting, this might be more interesting, and something I'm thinking of exploring in the future is that you could think of synthesizing an equivalent SQL query offline. You don't have to wait for the query to come in, and then it may be useful to apply these techniques. So the other related work is a couple of years ago that appeared in Sigmod. This also is a very similar goal, but uses static analysis to come up with an algebraic representation, which can be translated to SQL. But it turns out, in fact, we did prototype this. In fact, the author of this, the first author was interned with us, who was also a part of this Froid work. We tried to implement this, but it turned out to be more complex. I can probably go into the details offline as to why this was not suitable for us. The most closely related work, on which our the Froid the intuition of Froid is built upon this, is the paper on UDF decorrelation, which came out in ICDE 2014. So this paper basically takes the approach of saying, can we extend the apply operator to new, like whatever, have extensions to model these imperative constructs, and then again transform them into standard apply and use the same subquery decorrelation techniques to do it. The intuition of Froid is based on this work, but there are some differences. So in Froid we don't want to introduce new operators as well. We just directly map imperative programs into already existing relational operators. And then this work, as I mentioned, is part of cost-based optimizer. It was designed to be part of a cost-based optimizer, whereas Froid is designed to be a precursor to optimization. And then there are some other details which are not handled in that work, which Froid covers. So just to quickly go over the future work, we want to expand the language surface. As I was mentioning, we want to handle things like table variables, loops, and table valued functions and so on, which are current limitations of the work. And this is ongoing. And there are also some other ideas around extending similar ideas to languages other than T-SQL. And we are also trying to look at extending this for ML applications, where you can try to move some of these data wrangling code closer to the data by doing SQL translations, mainly for the use case of in-database machine learning. So with that, I'll just summarize quickly. I think I'm already running out of time. So we described Froid, which is a extensible framework, language agnostic, because conceptually there is nothing very specific to T-SQL here for representing and optimizing functions in databases. We show how you can transform entire UDFs into SQL, a form that query optimizer can understand and then use known subquery decorrelation techniques, and also get the benefits of compiler optimizations. So in summary, it allows the users to get all the benefits of UDFs without compromising on performance. That's our the goal. So before I conclude, I just want to put a plug. We are hiring, both at the Gray Systems lab in Madison as well as in the MSR India lab, Bangalore. So we are looking for full-time employees, interns, postdocs. So if you're interested, feel free to reach out to me. With that, I'm happy to take more questions. Thank you.
So let's take the questions offline because we're running out of time, and we have a student meeting right now in the database lab. So we do? Yeah. Yes. So right. So that's thank you, and then we'll.
Thank you.